In the 17th century, the world was viewed as a perfect clockwork mechanism. Sir Isaac Newton proposed that if we knew the exact position and velocity of every particle in existence, we could calculate the entire future with absolute certainty. This concept is known as determinism, the cornerstone of classical physics. It paints a picture of a universe that is fully predictable, stable, and orderly. However, this Newtonian vision is today considered a myth, a useful approximation that fails to account for the complex, chaotic nature of reality. In Newtonian physics, the universe is a clockwork mechanism. If we know the starting point, we should know the future. But complexity introduces a glitch. Think of a pinball machine. Precise initial hits remain predictable for the first few bounces, but quickly diverge. This is not randomness. The math is deterministic, yet small deviations lead to exponentially different futures. This is the mathematical glitch at the heart of our world. The butterfly effect is often misunderstood as magic, but it is actually a precise mathematical phenomenon known as sensitive dependence on initial conditions. In a system governed by this effect, two paths starting at nearly the same point do not stay together. Even the smallest, almost invisible difference at the start can lead to massive deviations over time. This exponential divergence means that the future state of the system becomes unpredictable, as the initial conditions are never known with absolute perfection. The Lorenz Attractor is a masterpiece of chaos theory. It is defined by three coupled nonlinear differential equations that map a path in three-dimensional space. These equations generate a trajectory that winds forever without ever repeating itself, forming the signature double-wing shape we see here. It is deterministic, yet fundamentally unpredictable. In a feedback loop, the output of a system is fed back into itself as the new input. This creates a cycle where the system constantly processes its own results. In linear systems, small inputs lead to proportional changes, resulting in predictable, straight-line growth. However, in nonlinear feedback loops, the math causes small differences to amplify. Two nearly identical paths diverge exponentially, making the future state of the system impossible to calculate precisely over time. How do we measure the speed of chaos? We use a mathematical tool called the Lyapunov Exponent. It acts as the clock of chaotic systems, measuring how quickly two nearly identical starting points drift apart. In a predictable system, points stay close, but in chaos, even the smallest difference grows exponentially over time. This is the formula for exponential divergence. Here, lambda represents the Lyapunov exponent. When lambda is positive, the distance between points grows indefinitely. A positive value is the definitive mathematical signature of a chaotic system. It tells us that our ability to predict the future is limited by the very nature of the system itself. We often assume that if we just had more processing power, we could predict the future with perfect accuracy. But in chaotic systems, this is an illusion. Even with infinite computing power, we face a predictability horizon. This is a fundamental law of nature, not a hardware limitation. The error in our initial conditions grows exponentially. Doubling our computer's speed might only buy us a few minutes of extra prediction time, rather than days or years. In the world of chaotic systems, we often encounter the precision paradox. We tend to ignore errors at the 15th decimal place, assuming they are insignificant. However, in nonlinear systems, these microscopic differences don't stay small. They propagate through feedback loops, growing exponentially over time. By the 15th iteration, what started as a rounding error has become the primary driver of the system state. In chaos, there is no such thing as an insignificant number. Predicting the future of a chaotic system requires perfect knowledge of its initial conditions, exactly where a particle is and exactly how it is moving. In classical physics, we imagine a particle as a distinct point with a specific path. We think we can measure both its position and its momentum with infinite precision. However, the Heisenberg uncertainty principle sets a hard limit. It states that we cannot know both the exact position and the exact momentum of a particle simultaneously. If we sharpen our measurement of position, the momentum becomes blurred and uncertain. The more we zoom in, the more the quantum nature of the particle fights back. This isn't a limitation of our technology. It's a fundamental property of the universe. Because we cannot define the perfect starting point, the long-term prediction of chaotic systems remains unreachable. At the quantum level, the very act of measuring a system to predict its future adds new variables. By trying to observe the system, we accidentally break its state. We see a wave-like system representing a quantum state. But when our measurement probe interacts with this system, the wave function collapses. This interaction isn't a mistake of our technology. It's a fundamental property of nature. The measurement forces a definitive state, destroying the predictive potential we originally sought. The atmosphere serves as our most visible case study for chaos. It begins with microscopic thermal variations on the ocean surface. A tiny change in water temperature might seem insignificant, but these small fluctuations act as the initial conditions for larger systems. These small variations cascade into massive, nonlinear pressure systems. The energy spreads outward, diverging exponentially. This sensitive dependence is exactly why long-range forecasts fail. A small error in measuring a heat bubble today determines an entirely different weather outcome weeks from now. To manage chaos in meteorology, we use ensemble forecasting. Instead of relying on one prediction, we run 50 models, each with a tiny, randomized variation in the starting data. At the start, these models are nearly identical, but because the system is chaotic, even microscopic differences cause them to diverge over time. The resulting spread visualizes our uncertainty. When the models agree, the forecast is reliable. When they diverge, the path ahead is unpredictable. Even with the massive growth in supercomputing power over the last few decades, our ability to predict the weather has hit a hard structural limit. While computing capacity has exploded, the reliable forecast horizon has only shifted by a matter of hours. This isn't a failure of technology, but a fundamental property of our planet's atmosphere, known as Lyapunov time. Lyapunov time defines how fast small errors in atmospheric measurements grow. Once these errors grow exponentially, they dictate the state of the system, making accurate long-range forecasts physically impossible. In the vast theater of the solar system, orbital stability can be deceptive. Take the Trojan asteroids, which share Jupiter's orbit. To the naked eye, these clusters appear locked in a perpetual, safe dance at the Lagrange points. They seem perfectly stable. However, orbital mechanics tell a more complex story. Over millions and eventually billions of years, tiny gravitational nudges from other planets introduce microscopic errors. Because these systems are nonlinear, these small inputs do not average out. They grow exponentially. What starts as a minor deviation becomes a large-scale shift. Over deep time, the Trojan asteroids are technically chaotic. Even the clockwork heavens are subject to the inherent sensitivity of initial conditions. In chaotic systems, predicting a specific future point is mathematically impossible due to extreme sensitivity. Even tiny errors in data grow exponentially, making point prediction fail quickly. New developments in AI allow neural networks to shadow an attractor. Instead of chasing a single path, the AI learns the overall geometry, defining the bounds of possibility. This shift moves us from trying to predict the exact outcome to understanding the structure of reality. Historically, we tried to predict the exact state of a system. We wanted a single point in time, a precise outcome. But in chaotic systems, the tiniest inaccuracy causes this path to diverge rapidly. Today, modern research has shifted the goal. We acknowledge that the exact point is unknowable. Instead, we map the probability distribution of all potential outcomes. By viewing the future as a distribution, we stop chasing a single, unreachable dot. We define a range of likelihoods, allowing us to manage uncertainty rather than fight it. This represents a major shift in physics, embracing uncertainty not as a failure, but as a fundamental, quantified property of the dynamic universe. In the study of complex systems, we've encountered a paradigm shift. We are no longer searching for a single precise future trajectory, as chaos makes that impossible. Instead, we now map the basin of attraction. By observing how a cloud of possibilities evolves, we understand the statistical future of the system rather than just one point. We often view unpredictability as a failure of our calculations, a glitch in the clockwork of reality, but this perspective misses the fundamental truth of our universe. A perfectly deterministic universe would be static, a repetitive loop where nothing new ever happens. Chaos, however, is the engine of novelty and growth. It is exactly because the future is sensitive to initial conditions that it remains open, creative, and uniquely our own. Certainty is not the goal, discovery is. The butterfly effect proves that the future is creative, not just a repetition of the past. Because the system is nonlinear, these small inputs ensure that no two futures are ever identical. Chaos is the engine of novelty. It reminds us that the future is not a predetermined replay, but an unwritten, emergent story. We are shifting our strategy. Instead of trying to force a single, perfect prediction, we now embrace probabilistic modeling. By running an ensemble of models with slightly different starting points, we map out a range of possibilities rather than a single destination. To keep these models accurate, we use data assimilation. This is the process of periodically resetting our path with real-world sensor data, effectively pinning our trajectory back to reality. By managing the chaos rather than solving it, we transform unpredictability into a tool for understanding complex systems. We began our journey seeking to predict the future. We hoped for certainty, like a clockwork machine. Yet we discovered that certainty is an elegant, unreachable ideal. It is a limitation of our map, not a property of the territory. Accepting the chaotic nature of the world is the first step in understanding the true complexity of reality. It is not a failure of our technology, but a testament to a dynamic, ever-changing universe.